Welcome. In today's video, we're going to find how PGFs can be used to evaluate the moments of a distribution. In this particular video series, this is the third video in the series of applications of probability generating functions. So without further ado, let's begin. Here is my original claim of how we're going to derive moments. For a random variable x, let's say with probability generating function px of z, the expectation of x times x minus 1 dot 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 times x minus 2 is equal to the nth derivative of the probability generating function evaluated at 1. This superscript n in brackets represents the nth derivative. And for avoidance of doubt, let me just rewrite this as dn on dzn px of z evaluated at z is equal to 1. Now, this will allow us to evaluate moments. In particular, notice that the expected value of x would be equal to the first derivative evaluated at 1, or in other words, I can rewrite this as px prime at 1, and the expected value of x minus 1 would be the second derivative evaluated at 1, or in other words, px prime prime 2, and therefore, if you wanted to evaluate the second moment, x squared, this is again the equivalent of the sum of x times x minus 1 plus the expected value of x. We've seen this result several times in other videos where if you were to expand the brackets here, you'd get x squared minus x, and then you get a plus x, leaving with the x squared. But of course, we have expressions now for each of these two terms. We said it was above, it was the second derivative, p double prime of 2 plus p prime of 1. So here is a first example of how the first and the second moment of x can be computed with PGFs. Now, keeping this in mind, I haven't really proven this fact yet. I've kind of just taken it as given. So let's actually go ahead and prove why this is the case in particular. So let's begin with the right-hand side of my equation. The right-hand side was the nth derivative. So the nth derivative at x evaluated at 1. And again, I said this was defined as nth derivative of the probability generating function evaluated at z equals 1. I'm going to use our definition of the probability generating function, which in this case is the expected value of z to the power of x. Say that that is evaluated at z equals 1. Now, keeping this in mind, we're also going to use our definition of expectation, and recall that the expected value of, say, a function of x is equal to the sum of x across its entire support of f of x times the probability mass function. At least this is true for a discrete random variable. And so the expected value of z to the x is the sum of z to the x times px of x. This, keep in mind, is the probability mass function. Apologies that the terminology looks so similar. Generating function and mass function look similar terminology, but this is now the mass function. So that's from x equals 0 to infinity, z equals 1, and we're still differentiating d on zn. Now, of course, the reason we're going from x equals 0 to infinity, because that is what probability generating functions are defined for in terms of their support. So, keeping this in mind, or looking at this expression, we see that we have a derivative of a sum of functions. So I want us to remind us some properties of differential calculus. In particular, I want us to have a look at the fact that if I take the derivative of, say, the sum of two functions of z, so the derivative of f of z plus g of z, this is the equivalent of taking the sum of their respective derivatives. And in the same way, if I take the nth derivative of two functions, or the sum of two functions, then that is the equivalent of summing their respective nth derivatives. And so putting that in mind, or keeping that in mind here, we're taking the derivative of a sum of functions. That is the equivalent of taking the sum x equals 0 to infinity of the derivative of said functions. And still evaluated at z equals 0. The next thing I want us to notice here is we're taking a derivative with respect to z. But px of x, the probability mass function evaluated at x, is independent of z. It doesn't depend on z. So therefore, it's actually a constant with respect to z. Now, with constants, I again remind you powers of different, or the properties of differential calculus. If I have a times f of x, sorry, I should say f of z, so not as to confuse you. If I say take the derivative of alpha times f of z, this becomes alpha times the derivative of z. In a similar fashion, if I say take the nth derivative, evaluate at z, and alpha times f of z, this becomes alpha times the nth derivative of the function. The constant effectively can come out the front. So here it's a constant, we can bring it out the front. This means we've got x equals 0 to infinity of px of x multiplied by dn on dz to the n, z to the x, again evaluated at z is equal to 1. Final part in our expression here is we want to evaluate the derivative, the nth derivative of z to the n. Oh, sorry, z to the x. So what's the first derivative of z to the x? Well, the first derivative is just x is a polynomial, or it's a polynomial function, z to the power of x. And when we're differentiating polynomial functions, we note that what we do is we bring down the power and then subtract 1 off the power. So that becomes x times z to the x minus 1. Now, if we were to find the second derivative of z to the x, then we'd have to differentiate the function above again. So differentiating the function above, again with a polynomial in z, we bring the power down the front, x minus 1, then we subtract 1 off the power, x minus 2. Now you might start to see a pattern emerge here. First derivative, we get a minus 1. Second derivative, we get a minus 2. So by the time we get an nth derivative, dn on dz to the n, we're probably going to get x minus n as the power. The other thing to note is that the coefficient seems to keep on multiplying by a product. It's first x, then x minus 2, x minus 1. The next one will be x minus 2, and so on and so forth. So what we have here, we'll get x, x minus 1, so on and so forth, until the very last term in the sequence, which is x minus n plus 1. You'll notice that this, while this might look complicated, or why is this the last term? Well, think about it here. When we had a squared, we had a minus 1. So taking a derivative with respect to two derivatives, we end up with a minus 1 as the last term. So taking an n, what we'd end up with the last term is rather technically really what we're seeing here in this little bracket here is we're seeing x minus n minus 1. That's really what we're seeing in the final bracket. Because, again, when the derivative is 2, the last term is minus 1. If you took a third derivative, the next term would be x minus 2, 1 less than the derivative power. Hence why we end up with x minus n plus 1 there. Not necessarily straightforward. But now that we have derived that, we can substitute it in our function, and that becomes px of x multiplied by x, x minus 1, dot, 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 x minus n plus 1, z to the power of x minus n, again evaluated at z equals 1. Now, one interesting point is that when z is equal to 1, z to the power of x minus n, right? 1 to the power of anything is always 1. So this term here at the back collapses to 1, leaving us with x equals 0 to infinity of the probability mass function times x, x minus 1, dot, 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 all the way to x minus n plus 1. And here is the kicker. What is this the definition of? This is a probability mass function times some function of x, and we're summing it over the support of x. By definition, this is the expectation of the function x, x minus 1, dot, 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 x minus n plus 1. And there you have it. Here is the proof, because this was equal to our left-hand side of the equation. So a very important property and a rigorous proof of why this is in fact the case. Now that we've done that, let us solidify this with a particular example. We're asked here, x is a random variable with the following probability generating function. 1 over 5 times 1 plus z squared plus z cubed plus z to the 4. Find the expected value of x and the variance of x. Well, in order to do that, we're first going to have to compute the first and second derivative of the probability generating function. So let's begin. The first derivative of the probability generating function is equal to d on dz of the probability generating function, which in this particular instance is d on dz of 1/5. 1 plus z squared plus z cubed plus z to the 4. Now, similar to expressions or similar to the arguments before, when you've got a constant and a derivative of a constant times a function, the constant can simply come out the front. And then you can just differentiate the function inside. So keeping that in mind, that gives us 1 out of 5 times the derivative of this inner function, which is the derivative of 1 is 0. The derivative of z is 1. The derivative of z squared is plus 2z. The derivative of z cubed, power down the front, plus 3, 1 off the power becomes z squared. And of course, the z to the 4 becomes down the front. And you've got z cubed now as your power. Then we also need to evaluate the second derivative with respect to z. This is, of course, the derivative of the first derivative of the probability generating function. So we're going to substitute in a derivative that we just derived, which is 1 on 5, 1 plus 2z plus 3z squared plus 4z cubed, which in this case now again, the 1 out of 5 is a constant. We can bring that constant in the front of the derivative, and then we can differentiate the function inside here with respect to z. 1 differentiated becomes 0, we leave it out. 2z when differentiated becomes 2. 3z squared when differentiated, the power comes down the front to give us 2 times 3, which is 6. And then 1 off the power is, in this case, 1. That leaves us with z to the power 1, or just z. And similarly, at the end here, the 4z cubed, the 3 comes down the front of the power, leaving us with 4 times 3, which is 12, plus 12. And then the z to the power of 3, whoops, accidentally deleted that. The z to the power of 3 here becomes z squared after differentiating. Now that we've evaluated that, we can find the moments of x. So recall that I wrote up here that the expected value of x was actually equal to the derivative or the first derivative at 1. So we can calculate that now. The expected value of x is equal to prime evaluated at 1, which is, in this particular instance, what's our function for the derivative? It is here, up the top here, but evaluated at 1. So we need to substitute in 1 into that. So it becomes 1 in 5. 1 plus 2 times 1 plus 3 times 1 plus 4 times 1. And when you evaluate that, it becomes simply 2. Similarly, we can work out the expected value of x squared, which I pointed out before had this particular expression. The sum of the second derivative evaluated, apologies, at 1, not at 2, evaluated at 1. And so keeping that in mind, we can say second derivative evaluated at 1 plus first derivative evaluated at 1, which in this case, here is the function or the second derivative. So we can plug a value of 1 in that second derivative, leaving us with 1 on 5, 2 plus 6 times 1 plus 12 times 1 squared, plus we already evaluated the first derivative. We said it was equal to 2, so we can just write plus 2. After a bit of algebraic manipulation, or a bit of computation actually, 2 plus 6 plus 12 gives you 20. 20 over 5 gives you 4. So that gives you 4 plus 2, 6 altogether. And so finally, we can calculate the variance of x. The variance of x, which is by definition the expected value of x squared minus the expected value of x squared, which in this case substitute in 6 minus 2 squared, which we both evaluated above, gives us 2. And so there you have it. We've now gone through an example how the probability generating function can be used to evaluate the moments of the distribution. We've also proven why that is the case. I hope this video was useful. Thank you for watching. I hope to see you in the next one.